Hey, Megan, just wanted to say hello.
Hey, Roy.
Wonderful to see you.
I'm super happy to be here. It's only been
you were
like 6 years since I talked to LPI last.
right. It was your intern presentation.
It was.
Yeah.
Welcome to those of you who have joined us already. We'll give people a minute or so to figure out how to log in and update their Zoom like I had to do unexpectedly. So we'll start in just a minute. Okay, I think general with people. So welcome everybody to this week's seminar. This week to be joined by Dr. Mantle. Some of you may have heard an LPI intern. I should say living in Tennessee, currently serving the planet Carnegie Science, Washington, D.C. Petrologist, evolution with applications for plant formation. How badly was I breaking up?
Yes, you're breaking up.
Now? I'm not hearing you guys now. We're in trouble. Quick. Okay, can people hear me now more clearly?
Yes.
I get it good. Okay. So we're very happy to welcome you this week, Megan. So Megan is a postdoc at the Carnegie Earth and Planet Science Lab, and she is here to present the seminar talk this week, which is entitled Exploring Mercury's Petrologic Evolution Through Experimental and Modeling Approaches. Thanks so much for being here with us, Megan, and through bearing with our technical difficulties at the beginning. So I will turn things over to you now.
All right. Thank you. And thank you all so much for attending today. This is such a cool opportunity. Yeah, like I mentioned previously, I was an LPI intern back in 2017. So it's cool to be back in this capacity to talk to you all. So yeah, I'm going to be talking about Mercury today, and you're going to see a lot of the different approaches that I take to try to understand, a natural system such as Mercury. So a lot of different things here, but I'm excited to talk about it. All right, so in terms of the flow of the talk, of course, I'm going to start with some kind of basic introduction and kind of some background information. But really, this is going to follow a very chronological flow in terms of Mercury's history. So we're going to be starting with the magma ocean stage from one of its earliest evolutionary stages and moving forward to the crystallization process and what occurs post-magma ocean crystallization. I also have this bar down here so you can kind of keep along with where we're at, but hopefully the flow of this should kind of make sense. All right, so Mercury, our favorite little planet close to the sun. It's a very unusual little planet. It has a large core to mantle ratio. So that means it has a very thin silicate crust, but that's what we're interested in, is that mantle and the crust. In terms of its composition, it has a very unique surface composition. So there's a fairly high sulfur content, about 4 weight %, and NASA's last mission to Mercury, Messenger, revealed that these are probably in the form of sulfides, maybe magnesium or calcium sulfides. And there's a fairly low iron content on the surface, which is interesting if we compare that to what we know of other planets in our solar system, such as Mars and the Moon, which do have fairly iron-rich lithologies. Mercury is also believed to be heavily reduced between IW-3 and IW-6, with IW being the iron wustite buffer. So very reducing, which of course can change the way that things behave in the silicate system. And finally, Mercury has some pretty geochemically diverse terranes. So if we take a look at this map, and this is a very basic map, I think there's probably at least 9 identified geochemical terranes on Mercury, some of which are associated with impact basins like Caloris over here, but we're going to be focusing on the 2 largest terranes. So the Borealis Planatia in the Northern Hemisphere and the heavily cratered terrain intercrater plains, which for all intents and purposes is the rest of the planet. So what's interesting about these 2 terranes is that they are spatially, temporally, and compositionally distinct from each other. The Borealis Planatia resides in the Northern Hemisphere. It's believed to be of this effusive flood basalt. And compositionally, it's believed to come from a Harzburgitic composition. So it's pretty depleted in calcium when we compare it to the heavily cratered terrain, which is believed to come from a larzolitic composition. So it has more of that calcium component. And in terms of their ages, the heavily cratered terrain is older. It's the oldest terrain on the surface of 4 to 4.1 billion years old. The Borealis Planatia, it's a little bit harder to constrain that age. We do know it's younger, but in terms of constraining that, it's a little bit more difficult because this is based off of crater counting, but it is younger. So this suggests that potentially the first billion years of Mercury's history was dynamic and that we had some interesting geologic activity on there. So this compositional difference is driving this main question of how can the interior structure of Mercury produces geochemical terranes. So all the information we have really is from MESSENGER. So what can we take from that information and how can we try to move that forward in our understanding of the planet and its formation? So as I said, we're starting with the magma ocean stage. So, this is just the very basic magma ocean model where you're starting with the undifferentiated body and you're melting it via these different events such as impacting and decay of short-lived isotopes. And then you get to the magma ocean stage where you have enough melting to cause widespread global melting. And this can lead to the differentiation of the core and the mantle and the crust. So what we're interested in is really what happens like after we've segregated the core material and we're left with this magma ocean, we're interested in this silicate evolution. You're going to hear me talk a lot about viscosity today because it is a really important parameter when we're thinking about magma bodies. So just in basic terms, it's just a rheological property that describes the fluid's resistance to flow. And this particular property is sensitive to temperature, composition, and crystal fraction. So if we take a look at what I have plotted over here, I have plotted the viscosity of a peridotite liquid and an andesite at 0.1 GPa over a range of temperatures. So if we just look at the temperature component of this for both the peridotite and the andesite, at the lowest temperatures, they have the highest viscosities, and you increase in temperature, and with each respective liquid, you have the lowest viscosity. So there's the temperature sensitivity there. And if we look at compositionally between the peridotite and the andesite, the main compositional difference is the silica content. So peridotite is very silica undersaturated, and andesite is this intermediate type rock, so it has an increased silica content. And you can see that with almost 3 orders of magnitude difference between their viscosities, that clearly makes a difference. So composition plays a big role in this. Crystal fraction, I'll get into this a little bit later, but when you start introducing crystals into a liquid, it takes it from behaving as a Newtonian liquid to more of a plastic. So we'll see that effect happening a little later. And so when we're thinking about viscosity, it can control the some processes within a magma body, such as crystal fractionation and convection. So with higher viscosity, you're going to have less convection, less crystal mobility, and you're going to see the inverse with low viscosity. So the basic terms that I like to describe it is if you have a jar of honey and a jar of water, and you drop a marble into each of it, it's going to behave differently. It's going to flow a lot slower through the honey than it will the water. And so that's just kind of in basic terms what we're kind of conceptualizing when we're thinking end member of the high viscosity and low viscosity and what's happening within these magmatic systems. So to dive a little deeper into the silica composition part of this, the viscosity can be related to the polymerization, which in our silicate systems is defined by the number of bridging oxygens per tetrahedral unit. So we have our silicate structure, the thing that makes all of our silicate minerals, that has a tetrahedrally coordinated cation, which more commonly than not is silica 4+, but sometimes it can be other things like aluminum 3+. And the polymerization is defined by how many of these you can link together. So if you have an isolated unit, you're going to have something that's very low in viscosity and low in polymerization. And if you have something that's very connected, it'll be very polymerized and high in viscosity. So that's kind of how that relation comes here. And we're going to see that a little bit with some of these Mercurian liquids. Okay, so let's get into the experimental part of this. So we tested two compositions that represented a late stage Mercurian mag motion composition. So our two compositions were, one was with sulfur and one was without. So if you remember, I said that there was a fair amount of sulfur on the surface. So we're testing the possibility that was indeed part of the bulk composition, but also testing the possibility that it wasn't. And we're also looking at a range of relevant FO2 conditions, very reducing conditions for mercury. So you may also note that looking at these experimental compositions that there's no iron in here. And that's because we tested an iron-free composition because of the very low iron content on Mercury's surface. This is a schematic of the experimental assembly that we were using. So we put our experimental composition in here and we have a little metal sphere. And it was either rhenium or tungsten carbide, depending on the composition that we were using. Rhenium would react with the sulfur. So in those cases, we would use tungsten carbide. And this is what we'd use to measure the viscosity. So this is our little experimental assembly. And this is the experimental setup. So this is looking into the hutch at HPCAT beamline 16 BMB at the Advanced Photon Source, Sargon National Laboratory. Some of you may be familiar with it. This is our Paris-Edinburgh press here. And this is where all the magic was happening. So on the inside, behind these two little cables are a couple of anvils that you put that little experimental assembly in. And then these cables are what provides the heat. So what's so great about this particular setup is that we can utilize the X-ray source at the beamline. And we have this high-speed camera over here that we could lower down. And once we turn the beam on, we can actually image inside of the experiment as it's happening, which is really cool because I think as experimental petrologists, we put something in and kind of hope for the best and then, see how it looks when it comes out. And in this case, you can really see how it's happening during the process, which is really fun to do. So we get our experiment in there, we get it up to our desired pressure, which we were testing between 1 and 6 GPa, things that are relevant for mercury. And how can we calculate the viscosity? So once we have it up to pressure, we do an incremental increase in temperature until about 200 degrees below the anticipated superliquidus conditions. And once we get to that point, then we can ramp up the temperature quickly. So we essentially flash melt the composition. And so that's what this video is showing here is this experimental process. So we took a video for each of our experiments, and this is how we can measure the viscosity. So we know the frame rate of the camera, we know the dimensions of the capsule. So what we can do is we can measure the position of the sphere as it's falling, and we can plot it up into a velocity profile. So we have distance versus velocity. What we're interested in is the peak of this curve, which is the inferred terminal velocity of this experiment. So we take an average value of this terminal velocity, and we can plug it into Stokes' law. So Stokes' law takes into consideration a lot of different parameters, such as gravity, diameter and density of the sphere, density of the liquid. There's also these two parameters, the wall and end effect. So these parameters are important for working in these finite systems, which this capsule is a finite system, because you might notice that as the sphere gets very close to the bottom, it starts to slow a little bit. And that has to do with how the liquid moves within this finite capsule. And so the wall and end effect can help correct for that. So once we have all of these parameters, we can plug in our terminal velocity value and we can get a viscosity. So we did this for all of our experiments, and we had 17 successful experiments. We had 12 successful sulfur-free and 5 successful sulfur-bearing. So panel A is the sulfur-free, and if we start there, we can look at the data, and what we can see is that we have a temperature and pressure sensitivity, where the low temperature, low pressure experiments have the highest viscosity, and as we increase in PT conditions, we decrease in viscosity. So it's a fairly nice relation that we see within this data set. Now, if we move over to the sulfur bearing in panel B, it's a much more constrained data set, and this was certainly not for a lack of trying. We did try to explore more of the pressure temperature space, but this was a very difficult liquid to work with. But within this limited data set, there does appear to be temperature sensitivity and probably pressure sensitivity as well. But when we look at this data at all tested PT conditions and compare it to the sulfur-free, it's lower in viscosity. And this was interesting because we thought that, well, if sulfur is in this really reducing system, it's expected to be an anion, a 2 anion. And it should primarily bond with network modifying cations such as calcium and magnesium. So if you're removing those from the system, you can allow that silicate portion to polymerize more. That was the hypothesis going in, and it appears that this is not quite the case here. So we wanted to at least look into this a little bit more. So there are different methods that you can use to look at liquids or amorphous materials. So you could use Raman microscopy, which you can do that on glasses, the recovered glasses, or you can do in situ analysis with the multi-angle energy dispersive X-ray diffraction, and that actually is with the PE press at the beamline. What I'm going to show you are two spectra that we took of the Raman of two different glasses. So in the red, we have sulfur-free, and in the blue, we have the sulfur-bearing. So pretty much immediately, you can tell that there are some differences with the spectra of these liquid. And it really boils down to these Q species. So Q species is the way to define the tetrahedral structures within these liquids. So Q of 0 is an isolated Q species. And as you increase, Q of 4 is a fully polymerized system. So all of these Q species are present within this liquid to some degree. Some of their peaks kind of shift a little bit. It's probably due to the pressure in the system. But if we take a look at just the first peak, for example, the Q of 0 with this isolated Q species, this peak is much more pronounced and defined within the sulfur-bearing liquid than it is in the sulfur-free. And if you just move up to the next peak where you are expected to have more polymerized species, this peak is much more pronounced within the sulfur-free than it is in the sulfur-bearing. So at least taking this analytical approach to try to look at these liquids, we're able to confirm what we're seeing is that it's clear that the Q species and the polymerization within these liquids is different. And that probably largely comes down to compositional aspects of it. Maybe it's the reducing nature. Probably sulfur plays a big role in this. There have been some previous studies that suggest that when you have sulfur in the system, that it could change the stability fields of minerals like forsterite and enstatite. So perhaps we're seeing some effect of that here. But at least we're able to confirm that what we're seeing within the viscosity data is just this difference within the polymerization with the Q species. So when we go back to the experimental data, one thing that we can do is we can create a predictive model, a predictive viscosity model. And we can do that by assuming an Arrhenius relation shown here. So we have each of our respective data sets with our pressure, temperature, and viscosity data. And we can run a nonlinear regression through each data set, and we can extrapolate a parameterized value for A, the pre-exponential factor, E, the activation energy, and V, the activation volume. So once we have these three parameterized values, we can plug in whatever pressure temperature condition that we want, and we can get a predictive viscosity. So here is plotted up our two liquids, the sulfur-free and the sulfur-bearing liquid, in comparison to other known materials. So now you can kind of get an idea of what this is like compared to what we know. So they do appear to bracket the andesite, which would be expected if we're working with more of this late stage magma ocean composition. But you can clearly see the differences between the viscosities here, where the sulfur-free is more similar to an andesite, and the sulfur-bearing, while it is a little bit more viscous than something like an alkali basalt, it is a little bit more similar to that. So now we have these predictive models, and now we kind of know what these look like compared to other liquids. So the next step is to take this and say, okay, we have our viscosity data, our understanding of the earliest magma ocean stage. So now let's take a step forward and evaluate what it would look like when we start to cool the magma ocean and crystallize it. So the first step to that is looking at the solidification timescale, so how long it would take for the magma ocean to cool. So some other results from MESSENGER showed that there were these low reflectance regions across Mercury, and the spectral features aligned with carbon. And so because of the reducing nature of Mercury, this is believed to be graphite. And due to the widespread nature of these deposits and their proximity to impact basins, it's believed that this could be remnants of a graphite flotation crust. So we want to test the possibility that maybe there was a flotation crust. So when you have a flotation crust, and this scenario is very analogous to what we believe happened on the moon with the anorthite flotation crust, but you now introduce this conductive barrier. So it takes a lot longer for the heat to conduct through that lid and be released into the system. And so in this instance, you're going to have a more elongated solidification timescale. So our estimates are about 3,000 years for this particular scenario. And we're also looking at a 1 kilometer thick graphite flotation crust. This can vary depending on your estimates for the carbon content on Mercury. Maybe it's a little bit more, maybe it's a little bit less. If you have a thinner crust, it'll be a shorter solidification timescale. And conversely, if you have a thicker crust, you have a longer solidification timescale. But for the purpose of this work, we're going with a 1 kilometer thick crust. But if you don't have a flotation crust, then you don't have this barrier around the surface. So you can just radiate heat out as a black body. So it's going to be a significantly shorter solidification timescale. And so this estimate is a couple of orders of magnitude less, about 20 years. So now we have kind of these end member boundaries in terms of what we could expect for the solidification of Mercury's magma ocean. So armed with this knowledge, the next step is to look at some possible grain sizes that could grow during the magma ocean and during these cooling time periods. So we utilized experimentally determined grain growth laws for olivine, pyroxene, and plagioclase, so the common mafic minerals. And essentially, we're estimating what could be the upper bound of these grain sizes that we could expect within the cooling magma ocean. So once you have this information, the next step is to essentially evaluate what type of crystallization process you could expect within this magma ocean. So we are utilizing this critical grain size boundary. So it's essentially a boundary that defines at which point your system goes from entrainment to fractionation. So if your grain sizes are small enough and the density difference isn't great enough between the crystal and the liquid, they will remain suspended within the liquid, and you end up with this entrainment type scenario, which is like batch crystallization. If you have grain sizes that are large enough, the density is great enough from the liquid, between the crystal and the liquid, that they can efficiently fractionate from the liquid itself. So this, depending on the type of density of the liquid, you could have sinking. So if it's denser than the liquid, you have sinking. But if you have something that's lighter, that's where you start to get that flotation process. So this is an important way to kind of define what type of crystallization process we're looking at. And finally, the final step to this is evaluating how the liquid evolves during crystallization, because as I had said in one of the first slides, is that when you add crystals into the system, it no longer behaves as a Newtonian liquid. And so we can use this Einstein-Roscoe equation to model what the effective viscosity would look like as you increase the crystal fraction in the system. And so you can see just based off of the setup of this equation, it changes quite dramatically when you start adding them in. So we have all of these different steps, all of these different models that we're trying to incorporate. So let's put this into what it means for the big picture. So over here, we have the scenario with a graphite flotation crust on the left side, and on the right side, we have the scenario without a flotation crust. So this is just a snapshot at 1 GPa in the mantle, looking at what happens with olivine and the pyroxenes. So these colored lines here are the critical grain size boundary. So above these lines, you have grain sizes that are large enough and the density difference is great enough that they can fractionate from the liquid. Below this line, you have small grain sizes and they will remain entrained. So that's what these colored lines are. And here we have our evolution of our viscosity. So again, we're evaluating what it would look like in a sulfur-free and a sulfur-bearing scenario, and how that viscosity evolves when you add crystals into the system. So starting with 2.5%, 15, all the way up to 50%. And how that changes with the grain sizes that we have in the system. So starting with the graphite flotation crust, you can see that the solidification timescale is long enough that you can create grain sizes or potential grain sizes that would be large enough that they would fractionate from the system. So we would expect fractional crystallization to occur with this scenario. If you go to a scenario without a flotation crust, because you have such a short solidification timescale, the grain sizes will be so small that they will remain entrained within the liquid. So in this case, we would expect something more along the lines of batch crystallization. So in regards to the different types of flotation crust, if you have a thinner flotation crust, you'll probably be closer to the boundary between fractionation and entrainment. If you have a thicker crust, you're going to be further up into this fractionation regime. So that's kind of how it would look with that scenario. But again, we're just going with the fractionation here with the 1 kilometer thick graphite flotation crust. So just to kind of put it in a simplistic term, if we don't have a flotation crust, we would expect something that is primarily homogeneous in composition. But if we have a flotation crust, we could expect a fractionally crystallized mantle where we're developing these compositionally distinct horizons within the mantle. So if we go back to this map of Mercury and look at, in particular, this more complex mantle scenario, we look at the Borealis planatia, which is believed to be of a Harzbergitic source. The Harzbergitic source is produced within this predicted mantle scenario. But for the heavily curded terrane, this layers-lytic source is not. So that leads us to the next question of, could there be other processes that occur post-magma ocean solidification that could lead to creating some sort of layers-lytic source? So we started with modeling the densities of the different types of minerals we would expect in Mercury's interior using the third order Birch-Moynihan equation of state. So we're looking at our silicate minerals again, the olivine, orthopyroxene, clinopyroxene, but we're also introducing sulfides into the mix because now, again, we want to consider what is the possibility, what is the influence of the sulfides within the interior. So we have our calcium sulfide oldamite over here. It's less dense than our common silicates. And then we have troilite, which is an iron sulfide, and that's representative of basically the upper bound in terms of the density difference between the sulfides within Mercury's interior. And it is quite a bit denser than our silicates. So if we take these modeled densities and predict what this would look like in terms of a density structure in Mercury's interior, this is what it would look like for the scenario with just silicate minerals. We're not introducing sulfides yet. And I have kind of this gray region down here because the core mantle boundary or kind of the pressure depth of Mercury's mantle, there's been some suggestions that maybe 5.3, 5.5, maybe to 6. And some of the older papers I've seen closer to 9. So there's kind of some variability in terms of the depth, but probably, 7 is even really pushing it in terms of the depth. So that's why it's kind of in this gray region. But this is just showing what the density profile would look like within this fractionally crystallized mantle scenario. So I want to point out these two regions right here between the pyroxenite and the Harzbergite, and then the Harzbergite and the dunite. So these we have density instabilities where this overlying layer is denser than the underlying layer. And that comes down to the CPX in the pyroxenite and the OPX in the Harzbergite, because they're denser than the olivine and the orthopyroxene respectively. And this density instability is the first necessary step needed to start the process of cumulative mantle overturn, where that denser material sinks into less dense material to create some sort of gravitational stability. If we add sulfides into the mix, this starts to change things quite a bit. So there's been some studies suggest that maybe there was up to 10% weight of sulfides in the interior. So what I'm showing here is not saying that there is 10% of sulfides in every single layer. It's just showing what would happen to each layer if you added up to 10% of the high density sulfides or some of those low density sulfides. So if we look at between the pyroxenite and the Harzbergite, if you add in a significant amount of those high density sulfides, you could greatly exaggerate some of the existing density instabilities. But conversely, if you add in a fair amount of the low density sulfides, you could eliminate those instabilities altogether. So now it comes down to the question of, well, what would the sulfide precipitation look like in Mercury's interior? Well, we don't really know, but we can start to make some predictions as to what it could look like with the knowledge that we do have. So first, of course, composition is the first consideration of just really how much sulfur was present in Mercury's interior. Was there enough to have a significant amount of sulfur in there? And additionally, if you did have something like an iron-bearing sulfide, how much iron was there? Because we don't see a lot of it on the surface. Does that mean it's locked up in these sulfides, or just there wasn't much in the silicate composition to begin with? And of course, the alkalis, because this is important for the some of those lower density sulfides. So really, how much of all of these are present is kind of the first question that we should be asking ourselves. But the oxygen fugacity conditions can make a difference in terms of controlling when sulfides would precipitate. So at the more oxidizing conditions, and oxidizing relative to mercury, something like IW-3, it's been suggested that you would have precipitation of iron-rich sulfides earlier within the crystallization sequence, so therefore deeper within the mantle. But if you had more reducing conditions, then it's probable that the alkali-rich sulfides would precipitate later and thus shallower within the crystallization sequence. And heat-producing elements are an interesting component into this, because oldamite in particular, and interfissurite as well, can hold a fair amount of these heat-producing elements, these incompatible elements, such as uranium, thorium, and potassium. So some of these long-lived radiogenic isotope systems. So if you're precipitating these sulfides, which maybe have a fair amount of these incompatible radiogenic elements, and you're crystallizing them into specific regions in the mantle, over millions of years, you could introduce a fair amount of heat into the system that maybe could start some partial melting and kind of change the rheology of some areas of the mantle, which is definitely an interesting consideration. But taking all this into consideration, the most likely stratigraphy for this would be having those high density sulfides lower in the mantle, and some of these lower density sulfides probably existing further up in the mantle. But redistribution of sulfides throughout the mantle could occur later, because just this initial process of gravitational overturn is not the only physical process that happens within Mercury's mantle. So it could always occur later, but at least with this current stratigraphy, this is what we're predicting. So one thing that we wanted to do was just kind of test what types of sulfides we could precipitate, because it's not really well constrained in a lot of ways. So we decided to take that sulfur bearing composition that we had from our magma ocean experiments and just test a crystallization experiment at 1 GPa. So we used the piston cylinder, went from a superliquidus condition of 1400 down to 1000 degrees C at a fairly slow cooling rate so that we could promote crystallization. And so you can see these two backscatter electron images here, and we were able to produce orthopyroxene, a plethora of plagioclase, fair amount of clinopyroxene, and in some of these interstitial regions with these darker gray areas was actually quartz. But you can see all of these bright spots across both of these images, and those are the sulfides that we're interested in looking at. So we thought, we're going to just pretty much crystallize calcium sulfide. That's kind of what we anticipated with this. And probably about 75% of what I identified was calcium sulfide. But what was interesting is that the other 25% about of the sulfides that I identified were actually this titanium bearing sulfide, which I thought was pretty interesting. And so these spectra here are energy dispersive X-ray spectroscopy. So this was done on the scanning electron microscope just to give us an idea of what we're looking at. So it's interesting to see that we have some sort of titanium bearing sulfide. Now it's not exactly a 1-to-1 ratio of titanium and sulfide, but it is interesting that we have a sulfide like this. And this could potentially be a slightly denser sulfide than some of these lighter sulfides that we've been considering. So this is definitely interesting moving forward, and maybe further exploration on the types of sulfides that crystallize in Mercury, I think would be very interesting. But with this experiment, we're able to pretty much confirm this gabbro type composition with some of these, this calcium bearing sulfide within the upper mantle. So it's a very interesting little project that we worked on there. Okay, so now we have these potential gravitational instabilities within the mantle. So we're going to model the possibility that maybe there was some sort of cumulant mantle overturn. So we're primarily looking at the pyroxenite and parsbergite because we're trying to create some sort of layers-lytic composition, and we're missing that clinopyroxene component with the orthopyroxene and the olivine. So we're testing these two layers to see if we can mix them together. So we're evaluating this within, about the first 100 million years post-magma ocean solidification, because that heavily cratered terrain is the oldest terrain. So we need to see if this process is even feasible to get started within a reasonable time frame. So we're looking at a lot of different modeling parameters. So we're no longer looking at viscosities of liquids, we're looking at them as solids. So they are significantly higher than what we had been previously looking at. We're also evaluating a wide range of possible layer thicknesses. So the layer thickness relates to the overlying layer, in this case, the pyroxenite. So kind of looking at a lot of extremes from something that's very thin to something that's extremely thick. And we're also evaluating different density differences. So this lower density difference of 30 kilograms per meter cubed relates to if we only have silicate minerals contributing to that density and stability. Now, the 300 kilograms per meter cubed relates to if you have, in the extreme case, a lot of this, heavy sulfides that are concentrated within a layer, what kind of density and stability would you expect there? And it's much more exaggerated in that case. So we're looking at a lot of different parameters that, could be applicable to Mercury's interior. So the first step is looking at the instability formation timescale. So how long it would take to go from basically this layered scenario to the formation of the instability. So we're starting that downwelling process. And so you can see the equation that we used up here. Again, we're considering all of these different parameters in here. But this figure over here is just a compilation of what this equation is telling us, where we have these different layer thicknesses and at which time scale they would format. So the thicker lines relate to a higher density scenario, the thinner lines are a lower density scenario. And we have mu0, mu1 are related to basically the ratio between the viscosities of these two liquids. So there's a lot going on within this figure, but if we look at these thicker layers over here that have a larger density difference, then you're gonna have instabilities forming very quickly on the order of thousands of years. And if you have a layer that's much thinner and has a much smaller density contrast, you could be forming on close to tens of millions of years. So there's quite a big difference between these, but really in the end, with all of these considerations, you could have thousands to, 90 million years in terms of the formation timescale. So we're still kind of, even on this extreme end, still kind of fitting within that 100 million year timescale that we're evaluating, but it certainly seems like within the parameters, it does seem to be possible that we could at least form this within a reasonable time period. So now we have to evaluate what the sinking velocity would look like. So we started the instability formation, and now we're moving into the sinking velocity, because if you don't have a lot of sinking, you're potentially not going to be mixing the materials. So you wouldn't really get that, layers-lytic composition that we're looking for. But conversely, if you have a really fast sinking rate with your instabilities, they could sink very quickly that you don't really have a lot of time to mix the materials. So kind of looking for a happy medium there. And so when we look at what this velocity equation will tell us, so we have the time and the sinking distance. So we have our velocities that are plotted here. And so we're looking at an 80 kilometer thick layer right here. So it's just kind of a snapshot. It's a little bit easier to look at. And we're also looking at a smaller density difference. So just evaluating, is this even possible within the smaller density difference scenario? And so on the slower end, you would have 1.8 kilometers per million years. So, maybe over tens of million years, so you could have tens of kilometers of mixing. But if you're looking at the scenario where you have basically no difference between the viscosities of the layers, you could have a very fast sinking rate. So over tens of millions of years, you're well down to the core mantle boundary. So, this at least gives us an idea that even within this smaller density range, that it's possible that you could get the range of velocities that are something that's very small to something that's very quick. And so it's possible that we could have a range of sinking velocities within the parameters that we put in. So over 100 million years, even tens of millions of years, you could have a fair amount of mixing depending on the type of parameters that you are considering. So if we kind of bring this back to big picture for Mercury and what this means for this kind of dynamic evolution. So the models predict that you could certainly have some sort of overturn process occurring within that first 100 million years that's due to these density instabilities. And that there could be enough sinking that could occur within a reasonable time frame to mix tens to hundreds of kilometers within the mantle. And considering how large the heavily cratered terrain is, you would probably need a fairly significant amount of mixing. And this overturn could reasonably occur within even these smaller density parameters. So that's definitely an important concept when we're trying to think about where sulfides exist within Mercury's interior. And so I didn't really get into the harmonics of these instabilities, but potentially having a single or very few large instabilities probably leads to more incongruent mixing. Maybe if you have several small instabilities, you have a lot more widespread mixing throughout the mantle. So that's definitely an important concept and something that we think a lot with the lunar evolution as well. But with that, I will start to wrap up some of the conclusions. So to start, we measured the viscosity of Mercury's magma ocean. So we did that on the Parasenberg press, and we looked at the sulfur-free and sulfur-bearing compositions. And we took those liquid compositions, and we were able to extrapolate that to what this means for the evolution of Mercury's mantle and predicting basically what the crystallization styles would be on different solidification timescales. And so, we have some different end members that we could expect in terms of Mercury's interior. And finally, wrapping this up with kind of what would happen if we had some sort of cumulate mantle overturn due to density instabilities, and is it feasible, and what could it potentially look like within Mercury's interior? And so, could we produce these different sources for the different volcanism that we see on the surface of Mercury? So with that, I'll just leave my conclusion slides up, and I will be happy to take any questions. Thank you so much for listening.
All right, thank you, Megan. That was incredibly interesting. So it looks like we've already got a question here from Roy Christopherson. So Roy, go ahead and unmute yourself. And then talk. Oh, he says, hang on.
Okay.
Okay, I'm here. Sorry. All right, your former intern advisor has a question.
Okay.
So in modeling the overturn, you now have a layered mantle that's solid, right? It's completely crystallized.
Mm-hmm.
So you're using viscosities to model the rheological behavior of these mixing layers. And my recollection is people who model mantle flow from the terrestrial mantle, they need to use a full constitutive flow law to model all of that, right?
Mm-hmm.
Arrhenius relation, all that stuff, function of temperature. Why are you able to get away with just citing a simple viscosity?
So we're looking at a range of viscosities, and we are taking into consideration viscosities that are relevant for Earth, as well as our understanding of the lunar and Martian mantles based off of seismic data. So the data that we are using is for mantle materials. And there have been some model studies that have looked at, maybe Mercury's interiors on 10 to the 21. So, it is taking a more basic approach, but, we just don't have a lot of information about Mercury's interior. So this is just kind of taking this step into evaluating it.
Thanks.
All right, our next question is from Tab Preisel. Go ahead and unmute yourself, Tab.
Hey, Megan, can you hear me?
Yes.
Hi, awesome, fun talk. That was great. So I kind of wanted to back up a little bit, I guess, relative to Roy's questioning, and ask you a little bit more about the starting compositions, which were pretty high in calcium and aluminum, which is also going to affect the viscosity. Not orders of magnitude, but maybe an order of magnitude. But I guess more importantly, in thinking about sort of the conception of the Mercury and magma ocean, and that these types of liquids with their calcium and aluminum abundances would be basically at or near plagioclase saturation already. And so thinking about, I guess, the silicate mantle being predominantly, Harzburgitic or Laerzolitic, what was sort of the rationale for those starting compositions?
So yeah, the starting composition, so we're looking at what happens like late stage magma motion. So basically the upper half of the mantle. So it is going to look a little bit different than what you would expect with something that is just a, bulk composition, dominantly mafic. But this was based off of taking like a chondritic type composition that we would expect from Mercury and basically modeling what it would look like if you kind of got to that certain evolutionary stage within the magma ocean. And basically that's the prediction of that composition there.
Thanks. I have several more, but I think we should move on. And I'm excited that we get time with you afterward. This is like really fun to have you here.
Awesome. I'm excited.
Great. We can circle back to have at the end if we've got some time. But for now, let's move on to Brian Balta. Go ahead and unmute yourself, Brian.
Hello, nice to meet you. I don't think we've met before. So let's see. Now I'm blanking on this. My goodness. Okay, so you spent a lot of time here trying to come up with a way to make a Laerzolite out of this stuff, and you did that because you, at the beginning, motivated this by saying the northern hemisphere lava plains and the southern hemisphere were fairly different in composition, and you, if I heard right, highlighted calcium as a big thing that's different between them. Okay.
Yes.
So one thing you didn't rule out to my ears, I apologize if I missed this, was you were easily able to generate a pyroxenite from your stack. How do you rule out that the higher calcium portion of this isn't just coming from a pyroxenitic layer that's remelting, and verify that it must be a Harzburgite rather than just from the pyroxenite you made anyway?
Yeah, I mean, that's a totally valid question, because that comes back to, kind of the scenario of if you had a dominantly homogeneous mantle, like, how could you get these different types of compositions from that? You could invoke different degrees of partial melting with that as well. So it totally is a possibility. It was just taking this different approach in terms of predicting that possibility. So, I mean, I think you could probably look at many different possibilities for Mercury, but that totally is a valid one to consider.
All right, then next we have Larry Nittler. Go ahead, Larry.
Hi, LPI friends. I got to thank Kelsey for tweeting about this talk, so I knew about it in time to come see it. It was a great talk, Megan.
Thank you.
To find to not see magnesium sulfide in your crystallization experiment?
No, we didn't, and it was something that I maybe expected. I wasn't sure if that was something that I would see, but we were predicting probably dominantly calcium sulfide, but I wasn't able to find any like dominantly magnesium bearing sulfides anywhere. So, which is interesting. And I do think that it would exist within Mercury. Just because we didn't see it in our experiment doesn't mean it doesn't exist. I'm sure it does in quite a large abundance.
Yeah, I had a memory, like a lot of the modeling work we were doing when we were first getting these compositions, the assumption was that it would be more magnesium than calcium, but I couldn't remember if that was based on experiments or just some thoughts. So anyway, the other thing was, I don't know how much you know about the hollows, but they're this weird landform that's on the surface of Mercury associated with impact craters, and there's these kind of depressions that are thought to be due to loss of volatiles. They're really hard to understand, but one possibility would be if there was, just like there's the graphite, be a layer of sulfides. Is that reasonable?
It's an interesting thought, because I know that some people, like in some previous papers, have suggested like maybe you don't have a graphite flotation crust, maybe you had something that's more of like a sulfide type crust. And because if you have some of these really low density materials, if you get saturated enough within the magma ocean, then they could float to the top. So not saying that that's necessarily what's happening, but you could get some of these sulfides or some sulfur deposits that exist that are shallower, closer to the crust. So I don't see why it wouldn't contribute to that.
Thanks. It's one of those things that keeps being sort of claimed without discussion of whether it's petrologically reasonable. So thanks.
Yeah.
All right, thanks, Larry. So next up, we've got Kelsey Preisel. Go ahead, Kelsey.
Awesome. I had a question about your two cases. You have the graphite flotation crust, which is insulating or nothing.
Mhm.
Have you thought about like a quench crust that would be insulating and like how that changes your results or the timescales?
You know, that's interesting because, you know, when you're looking at the evolution of just magma oceans in general, that is one of the possible kind of, you know, conductive convective lids that you could produce is, you know, if you just have this quench type crust. So, you know, it would be interesting to look into that, and you would have to, you know, it would be difficult to figure out the basically like the, you know, how the heat moves throughout that crust, because if you're looking at some sort of complicated silicate composition, it's not as easy to define. I think, you know, it would extend your solidification timescale more than if you didn't have any sort of flotation crust. But to what extent, I'm not exactly sure. I would have to think about, you know, what kind of parameters would be realistic for calculating that solidification timescale. But it is an interesting thing to think about, and you know, it could be relevant for not just Mercury, but you know, other planetary bodies as well, if we're not sure that they develop some sort of flotation crust like the moon did.
Cool. Thank you.
Thanks, Kelsey. Next, we've got a question from Brendan and Zurez. Go ahead and unmute yourself, Brendan. We're not hearing you if you're speaking. It shows you're unmuted though, so it's a step in the right direction. We're here to channel our friend Brendan, who we hope is with us. It's not coming through, Brendan. If you want to type your question into the chat box, or you can save it for a discussion that we'll have with the experimental group in a bit. Right, I think that's what we'll do. Any other questions from the audience? Still got a couple of minutes. If someone has a burning question, Tab, if you wanted to continue with one of your many questions that you have, then you're welcome to, or you can save it for afterward. While we're giving people the chance to do that. Oh, here we have a question from Laura Lark. She's curious what temperatures you assume for your density profiles.
The temperatures that we assumed. Oh, okay, I see. So you're talking about like the evolution of the Birch-Röntgen equation state, because that does consider some changes within pressure and temperature. So we basically took, you know, a predicted adiabat for Mercury. So I think it was like 0.1 degrees C per kilometer, if I'm remembering correctly. And basically just modeling how that temperature would change as we decrease in depth. So we started with kind of like just a starting temperature, which I want to say was maybe like 1,000 degrees C, and just modeled how that would change. It didn't change a lot because it's not a huge adiabat, it's not a very thick mantle, but you know, just kind of going off of those assumptions. But yeah, so that change in temperature is just based off of some predicted adiabats for Mercury.
Thanks. Okay, here's Brendan's question in the chat box now. He's wondering if you could talk about the potential effects of sulfides to modify viscosity in a 3-phase flow regime, bracket silicate melt, silicate crystals, and sulfide melt, end bracket. You mentioned an estimate on the bulk density, but what about viscosity?
That's a good question. Let me see, I'm gonna pull that up so I can also read it a little bit as well. Okay, potential effects of sulfides to modifying the viscosity. So, you know, we didn't see anything like, you know, any sort of immiscibility between the liquids, which is, I've gotten that question before of like, well, you know, if you expect them to bond with these network modifying cations, could you have some immiscibility? I didn't see any results of that. I imagine if you increase the sulfur content, maybe you would see some sort of immiscibility, but I don't think that's a factor in here. But it's, you know, you pose a very interesting question, Brendan, and I'd love to talk to you more about that. I'd have to think about that a little bit more, but it's a good question.
Great, yeah, we can talk about that more in our discussion group. Brendan just wanted to add that they're seeing a signal of titanium sulfide with the new sulfur Zanes measurements of mercury and melt composition. So it's great to see that you produced them in your experiments.
That is very exciting, because when I was scouring the literature, I found one study of like an N-type chondrite that had I think it's just TIS lawsonite, if I remember correctly, but that was like the only thing that I could find in that paper was from 2012. So I'm guessing titanium bearing sulfide's not that well known yet. So at least maybe in mercury they'll become more well known.
Yeah, I think Brendan's hard at work on that right now. So we'll have lots to talk about. All right, well, I want to give folks one last chance to ask a question before we move on to the next discussion group that we're going to have. Brendan's celebrating, I think that's what that emoji means. All right, well, if there are no more questions from the audience, let's take a moment to thank Megan once again for this really interesting talk. Thanks so much for being here this week, Megan, and speaking in our seminar. We really enjoyed having you here. Our next seminar is going to be at the end of March after LPSC, so you guys can stress about that for a while before our next seminar. And we're going to have a discussion group between Megan and our experimental petrology group here in Houston. We're going to stay on the line here, so we appreciate you all for coming, but we're going to close this out to a smaller group discussion, and don't be offended if I boot you out. It's not personal. All right, well, thanks again, everybody, and we'll see you all next time. And for experimental petrology folks, please stay on the line.